Welcome everyone on this today's on Things to Come webinar. Our guest speaker today is Professor YUAN Weimin of NAOC, the National Astronomical Observatories of China from the Chinese Academy of Sciences, who will talk about the Einstein Probe, the Einstein mission of the Chinese Academy of Sciences. And you can see him in the camera together with Professor Maurizio Falanga, the former executive director of ISSI-BJ. Maybe you know him already from his work here at ISSI-BJ or and at EC in Bern. Before I give them the floor so that we can start with the webinar, I would like to say a couple of words about ISSI-BJ and then we can start. As you might know, I'm Laura. I'm the PR manager of ISSI-BJ. ISSI-BJ is the International Space Science Institute Beijing, which was established in 2013 thanks to the cooperation between the National Space Science Center of the Chinese Academy of Sciences and the International Space Science Institute in Bern, Switzerland. We organize, either together with EC or independently, we organize a wide array of events, workshops, webinars, forums, international teams, working groups, because the mission of EC and ISSI-BJ is to advance space science studies, so contribute to the advancement of space science studies, to improve our understanding of space missions, their scientific objectives, and so on. And therefore, we also cover a wide array of disciplines in order to do that. Today, the topic is X-ray, so exploring the dynamic X-ray universe. But before we start, I would like to ask Professor Falanga if he can introduce our speaker of today to you, and then we can start. Thank you very much once again.
Thank you so much, dear Laura. Welcome to this today's seminar about the Einstein Probe, exploring the dynamical X-ray universe. It's a new mission. It's very, I have to say, innovative and at the forefront. It's a mission that we should learn to hope to see and to see the results in the future with breakthrough results. And I am especially happy today to introduce you Weimin Yuan. I think nobody else could introduce this mission better than the PI itself. So about Professor Weimin Yuan, he's the chief scientist of the high energy physics group at the Space Science Division, the National Astronomical Observatories of China, the NAOC from the Chinese Academy of Science. His research interests involves X-ray astronomy, mainly in the observational and experimental study of active galactic nuclei and high energy transients in general. He got his PhD in Germany at the Max Planck Institute for Extraterrestrial Physics, and afterwards he was holding several postdocs positions, very prestigious, I have to say, one at the JAXA in Japan, at the Space Science Center in Japan, developing the MAXI mission, which is on the space station, and a very prestigious postdoc position he was holding at the University of Cambridge in the UK, doing an X-ray as an X-ray astronomer. And he joined the Chinese Academy of Sciences in 2004, first at the NAOC in Yunnan Observatory, and afterwards he moved to the headquarters at the NAOC in Beijing. And he's the principal investigator of the Chinese Academy of Science Einstein Probe mission. So Weimin, the screen, it's yours, and we are looking very much forward to listen to your talk. Thank you.
Okay, thank you, Maurizio. Hello, everyone. Good day. I would like to thank ISSI-BJ and also Professor Ip for the invitation to give this talk at ISSI-BJ. Today, I'm going to talk about the Einstein Probe mission, which is a mission led by the CAS and also contributed by the European Space Agency and NPE in Germany. So Einstein Probe is a mission to explore the dynamic X-ray universe. So the X-ray universe is rich in highly variable sources, transients, and even violent explosions. And this is an X-ray all-sky image obtained by MAXI. And I can easily pick up a few examples to remind you what the well-studied variables, the transients are, For example, this is a well-known black hole X-ray binary, Cygnus XY. You can see highly variable. Here shows the brightness changes with time. This shows very rapid variability on time scales of seconds, even shorter. And this is a change of the brightness or light curve of AGN, which is a supermassive black hole accreting mass from the surroundings. And okay, this is a light curve of an X-ray nova, which is actually an X-ray low mass black hole X-ray binary. And this is one of the very first low mass X-ray binary, which was discovered during the early days of X-ray astronomy, when the system was in an extraordinary high state outburst. And actually, this is the way how most of the stellar mass black holes in our galaxies were discovered. And there are also transients on this map, which you might not be able to see. The well-known, the well-studied ones are the gamma ray bursts. They are the most luminous explosions or objects in the sky when they are exploded. And the gamma ray burst, they can shine from the gamma ray all the way to the X-ray band, and they are spectacular ending of a life of stars. Okay, so to detect this kind of transients and monitor variables in large numbers, we need X-ray instruments which have large or very large field of view. Okay, sometimes we call them all-sky monitor. These sources and to detect the detection and the study of these sources are very important to understand the nature and the physical processes of this kind of objects and the processes, and even important to understand our universe. Okay, so there is a rich history in monitoring the X-ray sky from the very beginning of the X-ray astronomy. So there is a desire to drive the instrument to reach a higher and higher sensitivity. As you can see that as a result, the detector is getting bigger and bigger from the early days of the 1970s, Bella 5B and South 3, and all the way to the current all-sky monitors, which are operating, which I show here in these green boxes. For the current detectors, they already have a very large size of its detectors, for example, reaching already several thousand square centimeter detectors. So it's very hard to get even larger ones. One thing we would like to, I would like to make a note is that most of the transients and variables detected by this kind of instruments are mostly galactic ones. Okay, those extragalactic ones are mostly very bright transients like gamma ray bursts, and there is a large population of extragalactic transients which have not been detected so far, and they are waiting for our discovery. And I would like to mention a few things. One is that all these instruments are actually non-focusing instruments, and they are mostly working in the hard X-ray band and the gamma ray band. And almost there is no dedicated transient science mission. They are either payloads on board some other satellites or missions for study gamma ray burst, for example. And so to detect the bulk of the extragalactic transient population, we need to go to higher sensitivity, but it's already very difficult to increase the detector area by simply using this kind of a technology, because you need really large space observatories or to detect them. Okay, it's already getting to the ceiling of such kind of technology. So we really need some new technology to do that. Okay, so I would like to say a few more words about the two current all-sky monitor missions. One is the SWIFT of NASA. So SWIFT has a wide field X-ray monitor, which is called the BET. So it makes use of the coded mask technology. It's basically a GRB mission. it detects GRBs at a rate of roughly 2 GRBs per week, plus about 0.5 other kind of transients. It's working in the hard X-ray band from 14 to 300 keV with a very large field of view of 2 steradian. And the next one is MAXI on the International Space Station, which is a mission of JAXA. It's a beautiful mission, although very simple. It makes use of this very simple pinhole or slit camera technology, and it detects at a rate of 0.8 transients per week, and most of the transients are galactic objects. And also, it monitors a large number of sources on the basis of hour or daily, as it scans the whole sky twice every orbit with its 1.5 hour. So these are the working horses in orbits currently to monitor our dynamic X-ray sky. Okay, so in recent years, some new kinds of high-energy transients have been discovered, which are of high scientific values. The first one I would like to mention is the black hole tidal disruption event. So these are the events when in the vicinity of a black hole, when a star it gets too close to a black hole, it can be tidally disrupted, and the part of the gas of star is accreted onto the black hole. And during this process, a giant flare in the X-ray and UV and optical can be generated, and you can detect them. And this is kind of events generated for the quiescent black hole, which is different from the active galactic nuclei. So this provides us a very good laboratory to study black holes in a quiescent state, or otherwise quiescent states. So with the tidal disruption event, we can study the demography of black holes in our universe to study how matters fall onto black holes. And sometimes these kind of events produce relativistic jets. So we can also study how jets form in black hole accretion system. High redshift gamma ray bursts in the early universe. They are very important objects because they tell us when the first stars formed, when the first black holes are formed. Because they can tell us also about the metal enrichment in the early universe and the reionization of the early universe. Supernova shock breakout. These are simply the first electromagnetic light emitted during a supernova event. Okay, in the X-ray band, it's very important, and they can tell us about the supernova physics and also the progenitor stars of supernovae. Very important and interesting objects are the electromagnetic wave counterparts of gravitational wave events. Okay. These are very, very hot topics these days. And now nowadays we have only one detected case, but they can tell us about what are the EM counterparts are and how the compact objects emerge, or even the equation of state of the neutron stars. And electromagnetic wave counterparts of neutrino events. Okay, it's very interesting. A few years ago, there was one detection jointly by a neutrino observatory and also the electromagnetic wave telescopes. And these events can tell us about how particles are accelerated. And very recently, a very interesting phenomena called quasi-periodic eruptions from both active galactic nuclei or even from center of quiescent galaxies. They are models predicting they are associated with extreme mass ratio spirals, which are thought to be the gravitational wave sources. So they are new developments. These are the new developments, and they are very interesting. But the number of detections of this kind of transients are very, very few. So we need large numbers of this kind of objects to understand the nature of these kind of transients. To do this, we really need the next generation of X-ray monitors to see both deeper and further into the universe, and also to see them at a high cadence. Okay, so this gave the requirements for the next generation of X-ray OSCI monitor. So they should be having a higher sensitivity, at least by one order of magnitude deeper than those in working in orbits now, perhaps even better if it can be 2 orders of magnitude. It should have a large field of view and basically roughly at 1 steradian. It would be nice to be working in a soft X-ray band because this is a very sparsely explored passband. Okay, and here on the right-hand side, I show the limiting flux or the sensitivity in units of milli-Crab. Okay, is 1/1000th of the X-ray strength of the Crab nebula with the exposure time integration for 1 day versus the energy band of the detector for the current missions. I plotted the X-ray and gamma ray emissions here. And in comparison, I plot the sensitivity of the Einstein probe. This is design and sensitivity. So we really need 1 to 2 orders of magnitude improvement in sensitivity in order to detect the faint X-ray transients and preferably working in the soft X-ray band. So as you can see from this plot, there is a huge new discovery space for the next generation of X-ray OSCI monitor like the Einstein probe. So we really need to increase the sensitivity to go down to the lower flux limit. But how? How can we do this? Okay, one, as I already mentioned, that the current OSCI monitors have already reached a very large detector area, about 5,000 square centimeter. It's very difficult to build even larger ones if you want to reach such a high sensitivity. So we need something new technology. So this is the X-ray focusing imaging, because the previous ones are all non-focusing instruments. Okay, so we really need X-ray focusing imaging technology. Okay, so let me briefly demonstrate to you how X-ray focusing imaging can improve the sensitivity. Okay, imagine there is an X-ray source here. You have an X-ray instrument with an aperture to collect X-ray photons. Since for long-focusing instruments, okay, there is no focus of the X-ray light. So on the detector plane, the X-ray photons will fall onto the detector plane within a so-called source spot. Okay, the size of the source spot is exactly the same as the size of the aperture of the incoming aperture to collect photons. On the one hand, you want to have a larger aperture because you want to collect more photons. But on the other hand, as the aperture increases, size increases, the spot source size also increases as well. So, for example, I asked my colleague to do this very simple simulation. We put in 100 photons from the source. Okay, there are 100 source photons within this circle. Okay, but since the source spot is quite large here, it's the full width of at half maximum is about 1 degree, corresponding to 1 degree in the sky in diameter. So all these 100 X-ray photons are distributed within this very large area, because there are always background currents associated or generated on the detector plane. Okay, by both charged particles or a diffuse X-ray cosmic X-ray background. So you cannot tell which are the sources or which are the background. So in this case, for very faint sources, it's very difficult to tell whether this is a real source or it's just due to the background fluctuations. But for the focusing imaging, okay, it's different because the light can be bent. Okay, so the light can be focused onto a very small source focal spot. Okay, in this case, in our simulation, it's only 5 arcminutes in diameter, corresponding the size to the sky. So with the same number of 100 photons, the source stands out clearly from the background, and it's very easily for the onboard computer or the computer on the ground to recognize this is an X-ray source. And in this way, a faint X-ray source can be detected. So this is a very simple demonstration telling you about why X-ray focusing can improve the sensitivity. Okay, but to reflect X-rays is to focus X-rays is very difficult. Okay, it's very hard. And X-ray can be only reflected by the so-called grazing instance, meaning that X-ray photon can be reflected only at a very small instance angle. Typically for soft X-ray photons, this is a few degrees on a very smooth surface. Okay, but we can do it. Okay, there is a so-called YUAN optics which does this job. So the incoming X-rays can be reflected twice by these shells. Okay, and the X-ray photons are brought onto the focal point. Okay, and you can add more layers of shells, so you can have a much larger light collecting aperture. So you can have a very small focal source spot, so you can have a very high sensitivity. So this is the working horses for the current X-ray astronomy. Most of the X-ray telescopes are built in this way. And the very first one of this kind is the Einstein Observatory of NASA, which was launched in 1978. It had 100 times more sensitivity than the previous satellite Uhuru. In this way, the Einstein Observatory revolutionized the X-ray astronomy. Okay, so now following that, we have many other X-ray telescopes built in the YUAN type, XM Newton, Chandra New Stars, EUCLID, and so on. But the drawback of this optics is that it can have a very small field of view. The field of view is as large, the largest is only 1 or 2 degrees. So you cannot build or sky monitor using the YUAN telescope. Okay. So fortunately, there is another X-ray focusing optics, which is called lobster eye Micropolar Optics (MPO) for focusing X-rays. Okay, so an MPO or Micropolar Optics is just a curved microchannel plate, curved in a spherical shape. Okay, on the plate there are many tiny square holes or pores, if you like. And each of the pores is pointed towards the common center of curvature. So when an X-ray photon comes, it can be reflected by the walls of these tiny pores, and also in the same principle of the grazing instance reflection. If the reflection number of reflection is twice by the orthogonal 2 walls of one pole, the photon can be brought onto the central focal surface. Okay, as shown on this red dot here. So if the reflection is only, the number of reflection is only once, it will be brought onto one of the lines, forming a kind of a cruciform arm. Okay. So for a point-like source, the PSF or point spread function is a bright spot with 2 cruciform arms. Since such an optics is basically spherically symmetric, which means that there is no major optical axis. So light in any direction can be focused in the same way. Okay, they are equal in the same way at different places on this focal surface, which is also a sphere, half of the curvature readers. Okay, so this is because this kind of principle, certain optics can have in principle a very large field of view. Okay, so the source A here and the source B here, they can be separated very widely. You can have a very large field of view. If you like, you can build optics with a field of view of up to 4 pi. So this is called the lobster eye MPO, simply because people got this idea from the imaging principle of the eyes of lobster, which have the same structure, okay, but working in the optical band. It's very interesting. Okay. So this lobster eye micropolar optics is actually an ideal optics for X-ray wide field monitors. So since they can be built into a very wide field of view, and the most importantly is that within this large field of view, the imaging quality is basically uniform. Okay, there is no vignetting effect like in 1:1 type, and it is true imaging. Okay. And it gives you a very good angular resolution. The current technology, we can get angular resolution as good as several arc minute. And it is optimized for the soft X-ray band. And they are of low weight because this kind of device is basically made of lead glasses. It's very light. So this idea was first proposed by Roger Angel in the US in 1979. And since then, it has been studied extensively, both theoretically and experimentally by a number of groups for many years. For example, University of Leicester in Europe, and NASA, and also RICAN in Japan. And at our institute, NAOC, we started to study this kind of technology more than 10 years ago. So I show you here on the right-hand side a measured X-ray image of the point spread function at our lab, and you can see the PSF is just a bright central spot with the cruciform arms. This is a characteristic shape of the PSF for lobster eye micropolar optics. Okay, since then there have been a number of mission proposals based on the MPO technology proposed and planned, and also some already being built. I would like to mention that the Baby-Colombo mission, which has this MIXIS telescope, which make use of this MPO technology, but not to build into a wide field, but a narrow field X-ray telescope. And I have to mention two pioneers in this field who have made a great contribution to the development of the technology and also the proposals of the missions, namely the late Professor George Fraser and Professor Neil Garris. So now time for the Einstein Probe mission of the CAS. Before that, I would like to mention, to remind you that actually the first X-ray observatory of the CAS is HXMT INSIGHT, which was launched 2017. It is working perfectly now and collecting data every day. And since then, we have been developing the Einstein Probe mission by making use of the heritage we developed by building the XMT INSIGHT. So the science goal of Einstein Probe mission is to carry out an X-ray all-sky monitoring to discover and to characterize high energy transients, and to monitor the variability of X-ray sources at sensitivity at least 1 order of magnitude or even better than the current all-sky monitors. So the original proposal was proposed for an X-ray all-sky monitor for the Chinese space station. The proposal, it was proposed in 2010, and 2 years later we put forward a formal proposal for a free-flying satellite, the Einstein Probe, and it was formally adopted by the CAS in the end of 2017. And now we are in the phase C, which is the performance validation for the payloads and the spacecraft. The planned launch date is 2022, the end. The lifetime, nominal lifetime is for 3 years with a goal of 5 years. EP is an international collaboration with ESA and MP, and we are very proud and it's our privilege to have ESA and MP in Germany joining our project. So the main science goals of Einstein Probe. Firstly, we would like to carry out a systematic survey of soft X-ray transients and the variability of X-ray sources at an unprecedented combination of high sensitivity and cadence. Among the expected transients to be discovered, we are particularly interested in two kinds. Okay, the first is to discover the otherwise quiescent black holes at almost all astrophysical mass scales and other compact optics by capturing the transient X-ray flares. Okay, in terms of massive black holes or supermassive black holes, they are tidal disruption events. The third one is to detect and localize the electromagnetic wave sources of gravitational wave events by synergy with gravitational wave detectors. Okay, since black holes and the gravitational waves are the two major predictions of Einstein's theory of general relativity, we named the mission after this great scientist. Okay, besides these science objectives I mentioned, in the surveys, we expect to detect various kinds of high energy transient and the variability phenomenon. I don't have the time to go through each of these, but I just briefly mention some of them, like X-ray flashes or luminosity GRBs, supernova shock breakout, and magnetars, fast radio burst, stellar X-ray flash, thermonuclear burst, black hole X-ray binaries, intermediate mass black holes, active galactic nuclei, and X-ray flares associated with neutron-neutrino events. And this causes periodical eruptions, as I just mentioned very briefly. So there is a very wide topic for Einstein Probe to explore for the dynamic and the transient X-ray universe. Okay, here I'm going to talk about in the next several minutes about the instruments and the spacecraft. So there are two kinds of telescopes. They are both focusing X-ray telescopes. So wide field X-ray telescope, WST, there are 12 modules of them. Okay, they are the lowest eye MPO-based technology. So it's going to be of a very large field of view. It's 3,600 square degree, which is almost 1.1 steradian. So the detection band is in the soft X-rays 0.5 to 4 keV with a very good spatial resolution of 5 arc-minute. So this is very good if you compare the spatial resolution of about the order of degree for the current sky monitor. It's really good. So by having this, we hope to reach sensitivity of at least several times better than the current sky monitors. This instrument is mostly developed as the CAS and with contribution for the test of the instrument by ESA. So the second is a follow-up X-ray telescope we call FST. There are two units just for redundancy. They are the conventional telescopes making use of the YUAN optics. It's kind of small field of view telescope with 1 degree or so, and working in the normal X-ray band from 0.3 to 10 keV band. The effective area is 300 square centimeter at 1 keV for 1 unit, with a spatial resolution about half an arc-minute on axis. Okay. The spacecraft is being developed in a CAS Institute, and we're going to have this onboard data processing capability and a quick slew and autonomous follow-up capability. So once a transient is detected, the spacecraft will slew to point FST to the newly discovered transient so that we can do deep follow-up observations in X-ray band with FST. The follow-up X-ray telescope is a joint effort by the CAS and with contributions from the ESA and the MP in Germany. Okay, WST. This is a figure of one module of WST. Okay, for one module, there will be 36 MPO plates equipped with 4 back illuminated CMOS detectors on the focal surface. Each has a size of 6 centimeter by 6 centimeter. It's a huge detector surface. Okay, so the development is by the CAS Institute, SITP, and also NAOC, plus the MPO from NVT, and the CAS and ESA are responsible for the test and the calibration. So it's very challenging to build such a kind of MPO wide field X-ray telescope. I just would like to mention a few challenges. The first, this is going to be the very first large field of view MPO telescopes to be built. In total, we're going to have more than 400 MPO plates. It's a huge one. Also, the detector, the plane is also huge. Okay, the size of the detector array is something like we need 48 CMOS chips, which each has 6 by 6 square centimeter. So it's a huge one, although it may not be the largest one in space telescopes. So it's going to be also the very novel use of CMOS detectors for space X-ray detection, as far as I know. And also working in a soft X-ray band is very trivial. It's very difficult. Okay, so to my mind, it's more difficult than working in a hard X-ray band. So here I show the effective area of the WST, taking into account both the detector and then the mirrors. Here I show the field of view of WST. Okay, it's 3,600 square degree. You can see it's a huge one. Each square represents the field of view of one of the 48 CMOS detectors. There are 12 modules. Each module have 4. Okay, so in the upper middle is the position and the position of the FST field of view is representing one. And as you can see, that the field of view is huge. It can cover almost a large part of the galactic center, galactic plane actually. Although the effective area is small, it's only 3 square centimeters, as I just showed on this plot, but it's the same effective area in any direction within the field of view. So there is this quantity which is called GRAPS, which is basically the product of effective area and the field of view. So this gives you a measure of the capability to do the sky survey or the monitoring. So here I plot the GRASP parameter for WST and in comparison with several other focusing instruments. As you can see, it's this largest so far, as well as concerning the future missions. So it's going to be very powerful in terms of sky monitoring. So the FST. So FST is a joint effort by the CAS, mostly led by IHAP, with contribution from ESA and MPE. So ESA and MPE contributes both to the mirror, the water-worn type mirror, and also MPE contributes to the PNCCD modules as well. And the FST is making use of exactly the same design of the Rosetta telescope, which is in operation now. Here I show the effective area curve for 1 unit. So the maximum is more than 350 square centimeter, around 1 keV. So it's also a very powerful telescopes for following up X-ray telescope for X-ray sky monitor. Okay, a few more things about the mission profile. So the satellite will be operating in an orbit of 600 kilometers, which has an orbital period of 96 minutes. It's a low Earth circular orbit with an inclination of 29 degrees. And there will be alert data quick downlink capability. So we're going to use two kinds of transmission routes. One is by the BEIJING system. BEIJING is the Chinese satellite navigation system. And the other is we are going to use the VHF network to be provided by CNES France. So by doing this, we can have very quickly the transient alert information received just minutes after detection. And then we're going to release the transient alert information immediately after receiving and make them available publicly. Okay. There is also the capability to send the command uplink very quickly to perform a target of opportunity observations. For the normal TOO observations, the time latency is less than 1 day, but for time critical TOO observations, it can be as short as less than 10 minutes or so. There are three kinds of operation modes for EP. One is the survey mode for WST, and so once a transient is discovered, it will trigger the autonomous X-ray follow-up with FST. We also have the target of opportunity observation mode for both FST and WST with command uplink. For the ground segment, the EP mission center will be built by NSSC of the CAS, and the ESA is going to provide 1 or 2 ground stations for telemetry support. And the EP Science Center is being developed at the CAS, mainly at NAOC and also at IHAB as well. So here I show basically the orbit of EP and also the field of view in the sky. Here is animation of the all-sky survey mode of Einstein Probe. During observations, we mostly point WST towards the anti-sun direction to avoid the sun. The sun is a very powerful soft X-ray source. So for each orbit, there will be 3 snapshots, each lasting for 20 minutes or so. Okay. So in this way, in 3 orbits, which is roughly 5 hours, WST can cover almost half of the sky, which is the entire night sky. So within 1 day, there will be about 45 snapshots or so. Okay, a very brief update about WST and FST status. So far, we have built and tested 3 QM qualification models of the mirror assembly or mirror module. And also, we built 2 complete qualification modules for the WST, okay, modules. So you can see these are the QM1 and also the focal plane detector developed at SIBJ, the CAS. And I would like to mention that for QM3, okay, we just had it tested at the Panther facility at MPE by our colleagues of MPE and ESA. I'm going to show you some very preliminary result. Here I show in the middle is the 1/4 field of view of the entire WST module, which is 9 degree by 9 degree. Okay, so the 1/4 of field of view of WST. Okay, so there are 11 by 11 sources in 11 by 11 directions. Okay, for each of them, we tested the X-ray image. So you can see one of the X-ray image. It's very good. So the full width at half maximum ranges from 4 to 5.5 arc-minutes. Okay. The most important thing is that across the entire field of view, although it's 1/4 of the field of view of one WST module, there was very little change of the imaging quality and the PSF. So it's very, very encouraging to us. I would say this is perhaps the very first image of the X-ray large field of view focusing telescope ever built. I'm not sure. I'm not very sure. Okay, on the right-hand side, I show the measured effective area at the penta. So the centimeter square versus energy. And I show both the measured data and also the model prediction. Okay, so you can see that the model predictions match the data very well. So this means that we are doing not bad job. So we are very happy about this. This was just finished just last month. The data analysis is still being going on. So for FST, so the FST has been developed at CAS jointly with ESA and MPE. So at IHAP, they have built an X-ray camera QM already with the detector module supplied from MPE. Here, I show a joint test of this thermal structural model of the mirror module together with the camera qualification module in the 100-meter line, 100-meter long beam facility at IHAP. And very good news is the qualification module, QM of the mirror assembly, the mirror module, which is provided by ESA and produced by Medullary, is to be delivered to CAS very soon. Okay, as you can see on the right-hand side, and at the bottom I show the lab spectrum from the cameras. So the satellite we have built the STM Structural Model being built almost 2 years ago, and the QM is to be completed and tested in the next several months. Here in the last few slides, I'm going to show you some simulation of WST survey for a one-day observation. So you can see that the X-ray sources are already detected. The brightest one is the SCO X1. Okay, so in one day we're going to have 45 observations. Okay, so in 3 orbits, about 5 hours, WST can cover most of the night sky. And in this way, in half a year, EP is going to cover the entire sky in half a year. And here is the simulated all-sky image. And also there are transients inside which you cannot see with eyes for the 1 year observation. Here I show some of the simulated images for short time scale transients. And in the bottom, I can show the X-ray monitoring simulation of LMC. Okay, so it's kind of X-ray movie in the sky. So I should mention that in several months' time, EP can reach the sensitivity of the Rosat all-sky survey. Okay, this is a comparison of the EP WST images with the previous one, or the current one, obtained by MAXI. So this is the galactic center region. As you can see that there is a significant improvement in the sensitivity and also the spatial resolution of EP. Here I show estimated detection rates for the selected classes of transients. Please be noted that the numbers are very uncertain because the models are not known. We simply don't know the models for many of them. So for tidal disruption events, we expect to detect several tens to 100 per year, maybe several of TDEs with JET. And for supernova shock breakouts, several tens per year are predicted. For high redshift GRBs above redshift of 6 or 8, we predict to detect several of them. But it's very challenging to measure the redshifts. We should remember that. And very interestingly, that we can detect a very large number of stellar flares a few thousand a year, and also EP can monitor the variability of AGNs for several tens on the basis of daily and on the basis of weekly for hundreds of them. And in total, EP will detect transients at a rate of several tens per week. This is, although it's very uncertain, this is a huge improvement compared to Swift and the Maxi. And since I'm running out of time, I'm not going to show the details. This is simulated detection of a nearby TDE, and we can see the light curve by WST and X-ray follow-up observations by FST. Okay, the EP consortium. So EP is usually led by the CAS and participated by ESA in the form of Mission of Opportunity and also by Max Planck Institute for Extraterrestrial Physics in Germany. And we are also currently discussing with CNES in France. CNES would like to provide the VHF network and the support to contribute to the EP Science Center. So we have a large team of more than 100 people. We have a very enthusiastic collaborations from Europe, and they were working together very happily. And here's a summary. So I hope I can convince you that the X-ray sky is rich in various classes of transients and variables. And the future of the monitoring of the dynamic X-ray sky is very promising, which is enabled by this lobster eye micropole technology. The Einstein Probe mission will be discovering and characterizing a large number of faint transients in X-ray and monitor source variability. And the follow-up observations by ground-based and space-borne telescopes are essential. And the synergy with other multi-wavelength and multi-messenger facilities offer a great science opportunity. I stop here. Thank you for your attention.
Yeah, still here. Thank you very much for the talk. We have plenty of users at the moment, around 1,000, who follow the presentation. And it's now the time for the question and answer sessions. And before I give the floor to Professor Falanga to moderate, I would like to remind everyone that in case you want to turn on your microphone and interact with Professor Yuan, that is possible. You just have to write in the chat box, I have a question, I would like to have my microphone turned on, and then I can do that for you. In case you just want to write your question in the chat box, that's also right. And Professor Falanga, I think I've already seen a question that was sent during the talk.
Yeah, he answered this. Well, the question hasn't been answered by the slides itself, but it was a question given by Miyamoto-san on how big is the effective area of the wide field camera, but it came then later in your slide. So I don't know if you want anyway to say something more to...
So about 2.5 to 3 square centimeter. It's not very small. It's not very large.
So more questions. You can write the question in the chat, or please raise your hand.
Yes. I see no question for the moment also on Bilibili. I don't know if Professor Ip, he should be still online, or you, Professor Falanga, have questions. Of course, that's...
Well, I have several questions. First of all, it's beautiful to see this mission, so congratulations once more. And so, of course, you are more interested in imaging and catching all these flares invented in the light curve. What is the time resolution of this light curve?
Okay. Yeah, please go ahead. Okay, the time resolution of WST is, so we can read out at a frame of 20 hertz. Okay, so it's 0.05 seconds, the time resolution, but the real time resolution will be limited not by the detector readout time, but mostly by the number of counts of photons, because of the small effective area of WST. So there won't be many photons to construct very light curve on very short time scales, unless the source is very bright.
So we have Peter Kretschmer raising his hand. Let's see if I can unblock his microphone. Or Laura, can you unblock his microphone?
Yes.
Yeah, I have to say for FST, the time resolution is very high. So it's a standard X-ray telescope.
So, sorry, the microphone is now unblocked for Professor Dr. Kretschmer. Now you should turn it on. I unblocked it. To turn it on, you can look at the I think you should be next to your name. There is like the icon of the microphone, or at the top of the screen. In the meanwhile, I see there are also Dr. Van Velzen says he has a question about public alerts, and I can also unblock your microphone if you want to interact. Yes, let me see. And then Professor Ip, he has written a question. Maybe in the meanwhile we can see with the question of Professor Ip while I help him turn on the microphone.
I can read it if you don't mind. So Professor Ip asked whether there will be a synergy between Einstein Probe and SWARM and other space telescopes. The answer is yes. Actually, for SWARM, we are now working with the SWARM team. Actually, the PR of SWARM is just besides my office. We're going to work out a more detailed plan to do more close symmetric follow-up, symmetric observations to how to make use of the two space telescopes, which will be launched with a large overlapping operational time. Yes, we will do. And for the other telescopes, for GCAM, surely we're going to do that as well for the Chinese one. But for the other international space telescopes, we haven't, but we hope we'll do it in the future. And also, in addition to space telescopes, we are very keen to work closely with ground-based telescopes because we really need optical and radio telescopes to do very quick follow-ups, especially for because the number of transients is large, and sometimes we also need very large ground-based telescopes to observe high redshift GRBs, for example.
Weimin, can you also say something about the public alerts?
I
don't know what is the question exactly.
Yes, this is a question about the public alerts. So, since we can get the alert information on transients very quickly, we expect to get them minutes after the events. So we plan to release the information of the positions, of time, simple light curves, and Hausen ratio of the alerts, the X-ray sources immediately through ATEL or GCM to encourage our colleagues all over the world to do promote follow-up observations. Yes.
I see Professor Dr. Kretschmer is now also on camera, and if you want to ask the question and turn on your microphone, perfect. We should be able to hear you now.
Yeah, sorry for the option. I may have missed it because I was disturbed the latter part of your talk.
Okay.
Will there be an access to the actual light curve data, like we can go to MAXI and get light curves? Because I will use that, I mean, the SwiftBAT and the MAXI light curves. Yeah, we have tools to look at that also for historical data, but so what's the policy on those data? Because for many sources, I mean, I'm interested in alert, but in basically following the history.
Yeah, we haven't really developed a policy for this, but the basic consensus among our consortium is that we should make available at least the light curves for both of the bright sources available immediately to general public, and people can decide. They can decide based on the light curve property to decide whether they would like to follow which sources. But I think this is very promising. I cannot guarantee at the moment, but we are working towards this direction.
Okay,
yes.
That's very reassuring. I mean, for a very practical point of view, a kind of REST interface, I mean, something on the web where you can make a trivial query for a source and get then the Einstein probe, whatever is made public light curve data in a machine readable form is extremely useful. Yeah.
Okay, thank you for your suggestion. Actually, we would like to hear more from the community about your ideas about our data policy as well. Yes, thank you.
Thank you.
I see there is also, sorry.
Well, we have one more question. It's writing, what is the budget for the mission from Andrew Jones?
Good. So the budget, so the budget is difficult question to answer because in China we have a different way of calculating budgets from the other agencies like ESA and NASA, and the net budget without counting the launch, without the grant segment, is something like more than $100 million. I would say, if I remember correctly, more than $100 million. Yes. I can't remember exactly, sorry. It's a bit complicated, but this does not include the cost of the labor manpower. Because, for example, I'm paid by NAOC, not by this project.
There was also now something very beautiful written from Professor Bonnet, who is also listening to your talk. I can read
my pleasure.
Congratulations for your excellent conference and for your enormous progress since the first time we met when you described Einstein probe to him, to Professor Bonnet in Beijing. And I was enthusiastic about the concept and the capability of the size. Without you and your continuous determination to make Einstein probe a reality, we would not be so advanced today. So I am very much impressed. Congratulations and good luck from Professor Bonnet.
Thank you. Thank you for your wishes.
Then there is one more question from Huaiyu. Is the detection of intra-cluster medium included in the aim, scientific aim?
Yes. No, actually, not in the main science objects, but we will point the FST to some of the targets during the survey of WST. So during the survey of WST, we point FST to some of the known active sources, including a cluster of galaxies, I'm sure. And also, after accumulation of the data of WST for some years, I think we can have also a very good data quality for some of the cluster of galaxies, especially for those with larger size, because we have a large, we have a very large, we have very large field of view, so we can have a very large number of photons accumulated.
Thank you.
Okay.
So, yeah.
I don't know, since I was fixing Bilibili, I don't know if the question of Andrew Jones was also answered. The one about the budget for the mission. It was, okay. Apologies. There was a problem on Bilibili, where we have around 1,000 viewers at the moment. And since it's, if you both agree, since it's 5 o'clock, and if we have no other questions, we can, since time is up, we can then maybe wrap up. And thank you very much once again, Professor Yuan, for the excellent talk.
You're welcome. A pleasure.
Professor Palanga.
Welcome.
Hope to see you soon here in Beijing, hopefully 2021, maybe not, but maybe 2022. And thank you everyone for being here today, both here on Big Marker as well as on Bilibili. Apologies to the ones on Bilibili for the problems we've had, some issues, but I hope that the presentation was anyways possible to follow it. And therefore, I would like to remind you actually that we have another talk next week with Professor Evgenya Shkolnik, if I pronounce the name correctly, on the SPARCS mission of NASA. The time is slightly different. It will be in the morning at 10 a.m. Beijing time because she's based in the US. So for the ones in Europe, as usual, we will have the recording uploading after the talk. So thank you very much once again, and wish you a good evening for the ones here in Beijing, and good afternoon for the ones in Europe.
Thank you.
Thank you.
Bye-bye.